and I get scared that it won't show my recording, so but we're good. Apparently they've included AI in Zoom now. That's right. So it'll track everything I say and make like a whole meeting notes for it at the end of it. That's kind of cool. It's kind of convenient. All right, I have. Oh, there we go. I knew it was. My brain was like, you're supposed to project something. Okay, I have our warm up.
Scalar projection or vector?
What, this guy? Okay, let me open this up. All right, so here is your warm up. Let me go like this, make it nice and big. We'll project it. Actually, it'll show in the recording here. All right, guys, so here's your warm up. It says you're given this vector field, which I graphed for you. That's the vector field for that guy. And it says, and then you're given this curve, and it's kind of hard to see it because it's probably red, and it's kind of, can you see it in the back? It's a triangle. It goes from here, goes up, goes down, and goes back where it started. Okay? So it says that's a curve C. Give for that given curve, this line integral equals 0. Agree or disagree? Think about it. Start using your past notes if needed. I'll play some homework. Oh yeah, pass it. Actually, before I collect more, pass up your homework. Pass up your homework. Thank you. Pass it up. Pass it up. All right, guys. So do you think this line integral should equal 0? Think about it. Cover some theorems. Use a lot of what we discussed. I want to use section 16.3 notes. That's when we discussed all this. That's where all the theorems live. Yeah. All right, what do you guys think? Any ideas? Jacob?
The vector field isn't conservative, so I don't think it's 0.
How did you confirm it was not conservative?
Because there's derivatives, partial derivatives, partial derivatives, and
Okay, so
dp.
this guy here?
dp over dy, dp over dx.
You're saying this is not true right here, right?
Yes.
Okay, let's see. What's the partial of p with respect to y? 0. And the partial of q with respect to x? Well, y. Yeah, definitely not equal to themselves, so it's not conservative. Okay, so you're saying it's not going to be 0. Could it be 0? We're just saying it's a curve that goes back to the original point, right? Correct. There was a theorem that said if f is conservative, is conservative, what must be true? If it was conservative, what must be true with closed curves? You guys remember?
It's not conservative, it's either not 0 or we can't.
For all closed curves, yeah, there was a little bunch of theorems, but connecting them together from 16.3, we had that if f is conservative, then this better equal 0 for every single closed curve. It's not conservative though. So what is the opposite? What is the false statement of this?
It's not conservative, it's not positive.
Remember I told you guys it says for all. So what would have to be true? What would have to happen for this to not be true? It won't be 0 for at least one closed curve, because then it won't be true for all of them. So maybe this is 1. Yeah.
Our exam, we tested on like this kind of logical thinking, or just in terms of this.
If it's in any of the review guides, yes. Put that way. I'll have to look at it. And then whatever we discuss on Friday as well. Okay, so let's see. So we basically have that it could possibly be 0 or maybe not. We don't know, right? We can't guarantee it is though, because it's not conservative. So let's go go back to when we defined the line integral, and like remember that the line integral, what was it measuring? What does it measure for you?
How much the curve flows with or against the vector field?
How much the curve, yeah, I need you guys to remember all that, okay? How much the curve flows with the vector field. If it flows against it, what kind of answer was your line integral? Negative. If it flowed with it, positive. And it's 0 when it's either like flowing with it as much as it's flowing against it, so it cancels out, or perpendicularly the whole time. Okay? So what do you guys think? Does this seem to flow? It's going this way. What about this part here? How much would it flow?
It's going towards.
Kind of going towards it here, right? But in here, it's maybe going a little bit against it. When y is 0, what happens to this vector field? You get x to the 4th comma 0, right? So what are all the vectors going to look like? Y is 0. So let's see. So see, they're flowing this way here. So the point is that we're not really sure, right? It's a little mysterious here, okay? But we can't guarantee that it's going to be 0. Okay, we can't guarantee it'll be 0. It could be or it could not be. We don't know if that's the existing one where it has to be 0. So let's see. So basically the theme of section 16.4 is going to be doing line integrals, but only on closed curves because of these kind of scenarios, okay?
So the answer is inconclusive at a degree of participate?
For now, yes. For now. We don't know. We don't have enough information because this doesn't help us out. And the way that the vector field looked, we couldn't really see if it was flowing with it the entire time, or we guessed it the entire time. And so we're going to need some new tools. So let's see how we're going to do that. So section 16.4, something called Green's theorem. Another theorem. Yay. So many theorems. All right, so let's do what do we know so far? Okay. The big theorem that we learned in 16.3 is if you had f, you check to see is f conservative. And if you do the homework, you'll notice that is kind of the theme of the question of 16.3 is f conservative. So you learned two different theorems, the 2D version and the 3D version. This was covered in 16.3. This was covered in 16.5. This one uses this test that we were just discussing. You wanted to see if the partials were equal to themselves. Remember, you needed your domain is open, simply connected. We still needed that. And then in 16.5, we did something else called a curl. And you wanted to see if the curl of the vector field equal to zero vector. That was this version's test. Checking that. And again, you wanted the domain to be open and simply connected. Is open, simply connected. Okay? And so if the answer is yes, either in this case or in this case, that it is conservative, what did it mean for f to be conservative? What must it equal?
A function.
A function. That's right. That means f equals the gradient of some function for some f. Okay? And the reason you care about that, as you see in the homework, is that with this, now you can use the fundamental theorem of line integrals. And that way, whenever I'm being asked to compute a line integral on this vector field, all I really need is this f is really a gradient. It's really the gradient of some function. So I just replace the f with the gradient of a little function f. And then to do the line integral, all I really need are the endpoints of the curve. And I need the little function f so that I can plug in the endpoint of the curve and the initial point of the curve. And then bam, I'm done. Okay? That's a summary of last week. With other stuff, there's more stuff, but this is the big part. And so like right now in the warm-up, that's kind of what we did. We were saying, is it conservative? But it fails this test. It didn't fail, it just means that it was not conservative. So we can't use any of this anymore, because f is not conservative. So then that's the question of this section is, what if capital F is not conservative? Is there another way to evaluate its line integrals? Its line integrals. Let's share my screen, right? No. Is there another way to evaluate its line integrals? Right, because if it was conservative, I can just do it doing this method, but it's not conservative, and I don't want to use a definition and do the plug-in R and do the dot product and all that. Is there an alternate thing I can do? And so the answer is yes, but only on special type of closed curves. If you guys take out your chapter 16 packet with all the pictures in it and go to section 16.4, there's some new vocab. Look at that stuff. Okay. So on that page, it's talking, the left side talks about curves, the right side talks about the regions that we discussed in 16.3. So let me show you what the curves part is. So there's some definitions here. The first one is, we're going to say a curve is simple if it's non-intersecting. Notice this word has nothing to do with holes, the way a region was simply connected, right? Simply connected meaning it was connected with no holes, a region. But a curve is simple if it's not intersecting. So for example, if I have something like this, or something like this, these are simple because they don't intersect them. They don't intersect themselves. Versus if I had something like this, or maybe I had a closed curve that did that, these are not simple. Okay. So we're gonna look at curves that are closed, like this one, meaning that they're loops, they loop into themselves, that are non-intersecting. Okay? Closed curves that are simple will be something like this one right here. A simple closed curve. This one's simple, but it's not closed. And these are not closed at all. And then the second definition is a little funky. We're going to say a simple closed curve has positive orientation if it has counterclockwise orientation. That's how the textbook says it. I hate it. It's like, what? How can I see counterclockwise with some kind of weird loop like that? So here's my way to help you understand that, okay? If it's closed, it loops into itself, and if it's simple, it won't intersect, right? So it'll have to look something like this. Like that, whatever it is. However it looks like though, I want you guys to notice that it's going to bound a region. It's going to bound a region. The curve itself will now be the boundary of a region. Okay? Of one region because it's not intersecting. Versus this one, notice that it's like bounding this region and then the smaller region. It's a little confusing. What's the region? So that's why we don't want it to intersect itself. So picture it like this. You have this bounded region now. We're going to call D, going back to chapter 15 notation. It's a bounded region. C is the curve. And you're going to have positive orientation. If you guys ever see those folks at the circus that walk on the lines? I don't know what they're called. They like walk on a rope, a tightrope. They go like that with a big pole or so. No? Okay. Some people are looking at me like, what are you talking about? Go to a circus. Check it out.
Tightroping.
What are they called?
Tightroping.
Tightroping. Thank you. Okay. So there's a person walking here, tightroping. And they need to walk so that their left hand is inside the region. Okay? Their left hand is inside the region. So if a person's walking this way, where's their left hand? Towards inside the region or outside the region? Outside the region, right? So if they're walking this way, their left hand's out here. It's outside the region. Okay? If that helps. If not, that's not what we want. I want their left hand to be inside the region, so they need to be walking this way, which it is counterclockwise if you look at it like this. Okay? So in my notes, let me write that down. So if you walk on the curve, your left hand is inside the bounded region. This is going to matter. This is going to matter because if it's going the other way, you're going to see in a little bit what we're going to do. Your answer is going to be it's going to be wrong. It's going the other way. You need to make sure that your curve is going in this region. Okay? Charlie.
Like, for example, in the bracket, will there always be arrows indicating the direction as well?
Correct. Everything for these line integrals is an oriented region. Sorry, an oriented curve. All the curves are oriented.
So you're actually getting that without the arrows, because you guys know this.
Correct. Usually they say, like the textbook will say R, it gives you the vector function R, and it'll say, you know, from like T goes from 0 to 5. That's describing the orientation. Yeah. Sam. Yeah. Lefty lucid. Uh-huh. Yep. Unscrew that curve. That's right. Left that tip. All right. If we have a simple closed curve that is positively oriented, and we're trying to do a line integral on this, okay, then we're going to be able to apply something called Green's theorem. Green's theorem. And this is what it says. It says, let C be a positively oriented, and then this is a little new here, piecewise smooth. What the hell is that? Piecewise smooth is fancy math for a finite number of corners. Okay? There's a finite number of corners, like a triangle has 3 corners. Let C be a positively oriented, piecewise smooth, simple, closed curve. Hello, vocab, Jesus. And let D be its bounded region. Like this picture here. For a vector field, F, this is only true, this theorem is only true for 2-dimensional vector field, okay? That has P of xy and Q of xy. If P and Q have continuous partials, then, oh gosh, so much buildup. Okay, that's highly specific, but all the homework problems will have that. Then, if I'm being asked to do the line integral, this is an integral we defined in chapter 16, right? 16.2. It turns out you're going to use the chapter 15 double integral and do a double integral over this region. And the function that you're going to double integrate is the difference of these two partials. No, it's so mysterious, right? Partial of q with respect to x minus partial of p with respect to y. dA. This is a chapter 16 line integral. And then this is a chapter 15 double integral. And that's where we're headed, okay? The end of this chapter is going to do that. It's going to bring in double integrals, and then later on it's going to bring in a triple integral. Okay, that's where we're headed. If f is conservative, what will this equal? If f is conservative. If f is conservative, these two must be equal, right? So then the function would be 0. So what's the double integral going to be? 0, which is what this was saying earlier. If f is conservative, that will always be 0. So it's still going to work, right? But now, if f is not conservative, then this will not be 0. And so now I can actually evaluate this line integral using this double limit, since we know this will not be 0. You guys kind of see that? Okay. So let's go back to the warm-up. Redo it, but let's use Green's theorem now to figure out what the answer should be. Let's see. So let's go back to the warm-up. Example, let f be what I wrote in the warm-up, which was x to the 4th and xy, and c the triangle below, and then use that to evaluate the line integral along that triangle. And then the triangle is something like there's one, that, this was C. Okay. All right, so let's see, can we use Green's theorem? Okay. Is the curve closed? It's closed. Is it simple? It doesn't intersect itself. Is there a finite number of corners? How many corners are there? 3. Okay. Is it positively oriented? Can I unscrew it? Am I doing lefty-loosey? I'm walking on it, my left hand is inside the region, so yes, it checks off everything, right? So let's see. Use Green's theorem. Let's see, the curve is simple. Check. Closed. Check. Positively oriented. Check. And then it only has 3 corners, so we're good. Most of, I believe, in the homework, all the component functions will just be polynomials, so they'll have continuous partials. If not, just be careful when you differentiate them. These are polynomials, so they have continuous. So then that means we can use Green's theorem. Okay? So let's see how we're going to do it. The circle would have it's completely smooth. So yeah, it's definitely, think of it like you can have no corners as well. There's some curves which you're not going to be showing in this class that have an infinite number of curves. Kind of like you guys ever see the stock market graph? That graph is infinitely undifferentiable, meaning it has no derivative anywhere. You pick a point and you zoom in on that point, it's still a curve that's going like this. And you pick a point, you zoom in on that point, it's still a curve that has corners everywhere. So every single point has a corner. And it's kind of funky. I know. Say it again?
This is stock.
Stocks. Yeah, for stocks. Yeah, if you guys look at the graph, they usually look something like this. So even though there's these jumps, when you zoom in on it, those jumps really look like this. And then you zoom in on it. So those are not finite smooth. But don't worry about that, okay? You're not gonna see anything with that. This is part of the theorem because it's a math class and we have to cover our asses. Okay? Okay, so yes, we can. So let's use Green's theorem. So therefore, when I'm being asked to evaluate this line integral, I'm going to convert it, and it's going to equal this double integral. Like that. So you got to go back and switch your brain to chapter 15. Okay? Let's do the function first. What's the partial of q with respect to x? With respect to, with respect to x, y minus 0. So the function you're integrating is just the function y. Okay? So this just becomes like this. All right. So this is d now, like this. So you got to go back to chapter 15, and then you got to figure out how am I going to do the bounds for d? Am I doing it a type 1 region, a type 2 region, and all that stuff? Do I use polar coordinates? All that you have to apply to this homework, okay? So is the region round at all? So what do we not want to use? You don't want anything that's polar. Spherical and cylindrical is for triple integrals. Don't worry about those yet. Okay? Yeah, keyword. So do we want to bound y first and then x, or x and then y? Let's see. If you bound y, right? Y is going to be bounded below by what? By the curve down here, and it's going to be bounded above by this line. This is at 1, this is at 1. What's the y-intercept of this line? 1. What's the slope of it? So this is really negative x plus 1. Okay? You have to find the line. So it's going to be bounded below by 0, bounded above by negative x plus 1, where x will range from what to what? 0 to 1. Like that. And then you're integrating with respect to y, and then with respect to x. And then you gotta go and integrate, right? Take the antiderivative of that with respect to y, 1/2 y squared, blah, 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 blah. That's in the notes. But you guys have been tested on that. You can do that. And then you're going to get an answer of 16. So was the line integral equal to 0? Nope, it was positive. It actually shows us that it, most of the time, will really flow with it. It'll really flow with the current. You guys want to do it? Okay, some people look very worried that we got positive 16. Let's just do it. X goes from 0 to 1. You integrate y with respect to y, so you get this from 0 to negative x plus 1. You plug in those values you plug this in here for y, you're going to get 1/2. Plug this in here. I'm going to rewrite this as 1 minus x squared minus 1/2 0 squared. So it just becomes 1/2 1 minus x. And so we get 1 minus x squared. Do a little bit of u substitution here, or you can expand it if you want. If you do a little bit of u substitution, we end up with negative 1/6 1 minus x to the third power from 0 to 1. And we plug those in. Oh, you're right. 16 was way off. Yeah. I saw a 1 and I saw a 6, so I'm sorry. Good thing we checked. Jesus. Otherwise, you're right. It wouldn't have made sense because then it means like it's really flowing with it. But when we saw on the graph, it wasn't as much. Yeah, you're right. Sorry. That makes more sense for that. Oh, I wrote it like this in my notes. Thank you. Yeah. And so yes, it's close to 0, but it's not 0. Okay. Let me give you a taste of what your thinking would be if when you take the final and I give you this question. Okay. Let me give you a taste of the thought process that you're going to want to have. Okay. The desirable thing is for it to be conservative, right? So our strategy here with this problem is for doing line integrals. Is you're going to want to ask yourself, is it conservative? For this problem, it's a closed curve. If it was conservative, what do we know the answer would have to be? It would have to be 0. Okay? So in this case, it was not. So now, let's say I did not want to use Green's theorem, and I wanted to use the definition. Okay? If I wanted to use the definition, I need to parametrize the curve, this triangle. But there's no way to parametrize the triangle because it's made up of 3 different line segments. So what you would have to have done is you would have to parametrize this line segment, and this line segment. Okay? You would have to break it up into 3 curves and break it up this way. Okay? So to evaluate the line integral using the definition, you would need to split C into C1, C2, C3, so that when you want to find the actual line integral, there's hella work. You have to parameterize C1, you have to parameterize C2, you have to parameterize C3 with 3 different R vector functions. And then you have to do the line integral for each one. And then add it together. See how much work that is? Just to get freaking 1/6, exactly. Nobody got time for that. So you don't want to do that, right? That's always going to be your last resort because of all this work. So as the rest of the chapter goes, you see which theorems are going to be useful for you, right? So for this one, I wanted to check this. That way I can see if it's conservative. And it was not. So then if I try to do the definition, nope, that's too hard. So then I want to now have a new tool. Can I use Green's theorem? If the curve is not even closed, the answer is no. You have to do this way. Yeah, like if the triangle did not include the bottom part, and it was just like this, then you can't use Green's theorem. Because it wouldn't, if it was just like this. It's not closed. So then there was no other option, and you would have to split that up into separate pieces like this. Okay? Which I know you don't want to do. Actually, let me leave it here. Okay, let me have you guys try one. Try it out. Okay, so I want you to start practicing using Green's theorem. Use Green's theorem to evaluate the line integral, where the vector field is, what did I give you here? It's e to the negative x plus y squared, e to the negative y plus x squared. And here's the curve z. Sorry, the curve c. It's the cosine wave, but it's bounded below this part here. So this is c right here, where this is the curve y equals cosine of x. And then remember that this crosses here, so this crosses there. Yeah, it has to do with the curl. When you do the curl, when we do the curl, there's something here, and then this one was right here. So, yes. Let me show you. I have it in my notes. Yeah, it has to do with the curl. So, 16.5, we run the curl. So what I was saying is, you get 2-dimensional, you can try it into 3-dimensional, and you can see the kind of like a vector. This guy is in the xy plane. All these vectors are in the xy plane. So if you give it a 3D, the z component will always be 0. So if I take the curl of that, we get 0, 0 coming back. So that's kind of where that comes from. Because this theorem is a two-dimensional theorem. There's a 3-dimensional theorem. It's going to be very similar. And instead of this, no, this looks at the flow, right? This is supposed to study how the vector field flows with the curve. Because the curve is closed and it's positively oriented. Remember that the curl was a tool that studies how the rotation is going on the vector field. And so the reason that this is used is because this is the curl of a two-dimensional vector. Yeah. I guess I'll go around. Let me know if you need help. So now this is your 2D region right here. So you gotta go back to all this stuff. You gotta bound Y first. You will need a configuration by points. Little IBP in this problem. Little IBP. Integration by parts. Oh, IBP. Correct. Oh.
So, wait. Oh, yeah, I can't.
Yeah.
Suffering.
Yeah.
Not too exposed.
Oh, right, that's the next one.
You know you want me to check your bounds. You can check with your classmates, see if you guys have similar bounds. IVP, yeah, good. We'll just remind you guys. It's been a minute. You need that IVP formula, here it is. Integration by parts. I wanted to throw one of those in there just to remind you guys. Stay fresh in there. Look up only if you want to see the answer, okay? Because some folks are done, so I just want to. Where? Here? These are subtracted, so I split it up into two intervals. These are the two, so you can take the two out. That way I could do IDT by itself here on this one. I use the half interval. Or the double. You can only split them up if if the function has terms for adding or subtracting, and then you split them up. But if these were to be multiplying, you can't just split it up and take that. That's amazing. You can multiply them out to distribute. Yeah, like this one. This is going to be reduced, but you can also multiply this out. That's going to be correct. This one over here. Oh, I got canceled, huh? Let's see. Hold on. This one? That's this one. This is this. That's 0. That's negative pi over 4. That's 0. And then this is negative times a negative is positive pi. With a negative. So this is positive pi because of this negative one. And then this becomes positive because of the negative pi. Let me zoom in on that bottom part. That's the juicy part, right? Total Calc 2 problem. I don't even know. Whatever that means. All right, guys, so hopefully you got negative pi over 2. It is pretty messy, so you got to be very careful with this one. Integration by parts with the x cosine x. Or you could have left the 2 in there, that's fine. And then this other one uses the half angle formula. Okay, I just have one last thing and then we're done with this section. One last thing. Some notation stuff, especially if you're gonna have, who's like doing a lot of physics? Who wants to take a lot of physics? Okay, so you might see this notation. You guys raised your hands so low, no, probably. So some quick remarks, okay? Let me show. I'm not sharing my screen. You guys can actually see. Yeah, okay. So some quick remarks. The first one is, what would you do on the homework if this was oriented clockwise? Okay. If it's clockwise, technically this doesn't work, right? But there is something that you can do to turn it into counterclockwise. Just reverse the inner, kind of, yeah. So there's this property that says if C is negatively oriented, which is clockwise, then what we're going to call is negative C is positively oriented, which means just rotate it in the other direction. And that way I can use Green's theorem on this one. Because now it'll be it'll be positively oriented. But by negating the orientation of the curve, this is the negative of the line integral that is negatively oriented. Okay? So actually, let me not put the negative here. Let me put the negative. No, let's put the negative. So this is positively oriented. This is negatively oriented. And on this one, you can use Green's theorem. Okay. So if this homework problem gave you a negative orientation, right? Everything you did, you would still do the same, but just stick a negative at the end of it. Because you've changed the orientation, so your answer needs to include a negative at the end. Exactly, yeah. So if on this example it was oriented clockwise like this, right? Then your answer is going to be like this. Okay? So then what was the answer? It was like negative pi over 2, right? So then it would be positive pi over 2. Okay? And then the other comment I had is for the physics folks. This is a notation comment. Some math books and some physics textbooks, they use this symbol as well. Yeah, you listen to that? Okay. So there's that. And the other way that they'll write this line integral is they'll write it like this. They use the partial symbol and then they use d. So this means positive oriented boundary curve of d, right? So like this is d. They're telling you to integrate over its boundary that's positively oriented. And this part tells you, oops, I forgot to put a C here. This part tells you that you need to consider C being a positively oriented curve. All right. So it's just all fancy notation to mean what we're saying, yeah? So that you can use green scale. Our textbook won't, I think our textbook might use that like on theorems, but like on the homework and stuff, it doesn't use it. So all these are kind of saying similar things. It's telling you, make sure it's positively oriented. That's what it's saying. The other thing that you guys should put in your notes is that this theorem, Green's theorem, is only for 2D vector fields. That's important. Only for 2D. We're going to do the 3D one next week. Exactly. There's 2D and 3D versions of all this stuff. Yes. Somebody was asking me while I was walking around, why this function? Why is this what the thing that you integrate? Okay. Jacob. Kind of. It kind of is related to that. Remember we talked about curl of a vector field? Remember the video I showed you where they were showing the curl? And I was telling you the curl is really a vector, but in the video they said, we're going to have the curl be a number. This is the curl of a 2D vector field. Okay? Which is why you're checking to see if the curl equals 0, therefore these two are equal to one another. Okay? And why is the curl related to this? Because remember that the curl studied rotation about a point. Well, this is looking at how the vector field flows with the rotation of a closed curve. So that's kind of how it's related, okay? I'm not going to go too deep into all that stuff, but I wanted to show you kind of why that function. Let's take a break. We're done with this chapter, or this chapter. That'd be nice. We're done with this section, and so then we're going to take a break from integration. Okay? That's either good or bad, depending if you like integrals. Come on. Parametric. So let's take a break. Come back at 2. Resume at, let's see, 2:05.
This is going on. You're actually understanding what I hear.
All right, section 16.6. Parametric surfaces. So like I said, we're going to take a break. It's going to be a little weird, but we're going to take a break from vector fields and integrals in this section. Because we're going to need this tool for this section after that. That's why it's kind of like a little off topic. Okay. What have we learned to parameterize so far in this class? Lines and curves, right? So let me start with what you already know. So we know that to parameterize a curve, we have a vector function that looks like this. So let's let R be x of t, y of t, and z of t. Parameterize a curve C. And let me remind you all the visual stuff about that curve. So let's say the curve looks something like this. Let's say it's oriented like that. Remember that, let's say this is x, y, z. You're thinking of t as time, and you plugged in a t value, And then remember, it gave you a vector that's like drawing, it's sketching the curve. Okay? The Disney Channel, yeah, the little Disney Channel marker thing. So when you did that, it gave you a vector that starts from the origin and it ends, and its terminal point is a point on the curve itself that has coordinates x of t, y of t, and z of t. And so that's why in this textbook, they say r of t is the point, but it really is a vector. You're just thinking of the point being this point. Yeah. Okay. And then remember that you had its tangent vector at that point going in the orientation, following the orientation of C. That was a derivative. That was, I think that was all chapter 13 stuff. That's as far as we'll go for this, okay? So here's the goal of what we're gonna do. What we're gonna do is now, instead of my wand drawing a curve, it's going to draw a whole ass surface, okay? And the way it's gonna do that, you guys ever, when you guys, I don't know if you did when you were taught, but if you took a class that talked about our planet Earth, there was longitude lines and latitude lines, okay? What we're gonna do, we know how to parameterize curves. So to parameterize a surface, we're going to parameterize its longitude and latitude curves. Okay, so let me motivate that with a drawing. You're gonna make like a skeleton of it, correct, of the surface through curves. Okay, that's kind of the idea. Okay, so we're gonna use all this here. And so the goal of this section is to parameterize surfaces by using vector functions still. We're still using vector functions, but of two variables. Instead of t, we're going to have two variables now. Two variables. And so we're going to parameterize, and this is not in the textbook. Okay? This is just my way of kind of saying we're parameterizing its longitude and latitude curves. Let me show you what I mean by that. So let's say you have a surface like that. So you have a surface like that. We're going to make a grid on it where there's this curve here, there's this curve here, there's this curve here. So we're kind of like making it like its grid version of these longitude, latitude things. And then that'll go in one direction. And then we have the other curves. Think of it as like its longitude curves going like this. It's a little hard to draw, but hopefully I'm making my point. Okay? Making a grid on it. And then a point, x, y, z, will now be parameterized by two variables instead of just t. By two variables, u and v. so that if I fix one of them, and I vary the other one, depending on how I fix v, it'll either sketch this curve, or if I fix v to be a different value, maybe it'll sketch this blue curve as u is varying. And then if I fix u and vary v, depending on where I fix u, it might sketch this black curve. If I fix u at another number, it might sketch this black curve. Okay? So let me show you. Let's go formal now. Let's go a little bit more formal. So this is more what the textbook says. So it says, let S be a surface parametrized by R of UV, because now it has two variables, where X is parametrized by UV, Y is parametrized by UV, and Z is also parametrized by that same UV. That means X will now depend on two variables, U and V, and same with Y and same with Z. Okay? Where the domain of this vector function, D, lives in the UV plane. We call S a parametric curve. Sorry, surface. Parametric surface. You guys open your little packet to section 16.6. The top picture shows you you're on the UV plane, you get some domain, and you're only going to plug in points UV within that domain. But it's a little mysterious how the surface is developed. Yeah. You're still in 3 dimensions, and here's where it gets a little confusing. This was easier to see because we saw it as time, right? And then I was giving you the little Mickey Mouse wand analogy. It's a little harder with this. Because you're in the UV plane, you have some domain, but then it's being plotted on the XYZ surface. Sorry, space, and then you're going to get some surface here. It's still a vector. It's still going to be a vector drawing your surface, but what controls the vector are the points U and V. Let me put an example, and then let me answer that question, because it's a little abstract right now. I want to give it like something a little more tangible. So let's see, what does the surface? What is the surface of R of UV, where X is 2 cosine U, Y is just literally V, and Z is 2 sine U look like? Okay, so let's take a look. Notice in this case X and Z both use the same variable, U, right? Y is like the different one in this case. So what I want you guys to notice is X of UV in this case just equals 2 cosine U. It doesn't even use the letter V, but it can. Y UV is just V, and Z of UV is just 2 sine U. So if I only deal with x's and y and the z's, what happens if I square x and I square z? What happens if I square these two? Times 1, 2, 4. This becomes 4 cosine squared u plus 4 sine squared u. Factor out the 4. And what do you end up with inside? Cosine squared u plus sine squared u, which is just 1. So it's just 4. Okay, let me stop that. So see these grid lines here? Okay. What do you if I look at in the perspective of the xz plane, what does this describe? Circles of radius 2, right? Circles of radius 2. But so then you're going to get circles of radius 2, but then y changes depending on the value of v. So let me show you what's happening. Let's see if I can just squish it up to here. Okay, so watch. So if I look at it in the xz plane, I'm going to get circles of radius 2 like this, right? But depending on what I choose, right now, I can't use v on Desmos. I have to use k. So if I vary k, what do you think that's going to do to this circle? It's going to affect the y coordinates, right, of all those points on that circle. So notice that it'll just move the circle up and down. So as v varies, the circles are going to vary depending on the position of the y value. But in terms of x and in terms of x and z, they have to be circles because of what we just discussed here. It has to always be a circular curve with respect to x's and z's. Okay? So think of it like this. Think of it like if I parameterize this guy here, 2 cosine t, 2 sine t, and let's say I put let me let k be 2. So you guys see that curve? That's this curve that you guys had to do in chapter 13. It's a circle radius 2 where y is 2. That's this guy right here. Like that. But if I change this to a 5, now it's the same circle, but it's just positioned where y is equal to 5. And so that's what I was trying to say. If I fix the v to be a value, it'll change depending where the circles are. Okay? But now what if instead I fixed u? And so where is it? Oh, it's down here, you can't see it. What if instead I went with this? Let's say I plugged in 0. Like that. That would become what? It would become 2t0, right? What do you guys think the curve of that would look like? What's the only thing varying? Y. The only thing varying is the y. X is fixed at 2, and this is fixed at 0. What do you think that curve would look like? It's going to be a line. It's going to be a line so that x is always 2, z is always 0, but y varies like this, right? So let me what did I let here? I let this be 0. So let me go to 0. Let me do this one. That's the line where x is 2, z is 0, but y varies, right? If I change the value of this, that's going to change the value of these two. But it will still be a line. It's just going to be somewhere else. It's going to be somewhere like that. So I can't do this on decibels, but imagine there's a grid of all the lines and all the circles together. What do you think that surface would look like? If it's just varying like this. It's going to be a cylinder. That's the surface that we're parameterizing. Okay? Yeah, it's challenging. It's going to be a little challenging. Oops, sorry. Turn this off. Okay. So let me just add that here. So let me keep going with this. Stop sharing my screen. Okay, so what this gives us here is that it's circular curves of radius 2 that shift depending on the value of v, which is really the y coordinate. And so we were to kind of get a sketch of this. Do the grid beyond what you do. So then I have all these circles of radius 2, kind of like this, that move in the direction of the y-axis. And then I have the lines that we were looking at that move, that are parallel to the y-axis like this. And so yes, notice that we end up getting so. So this is a cylinder surface. The lines are determined by what you get when you fix either u or v. If I fixed v, right, then this is going to give me 2 circles. That would be like this guy here. It's going to give me circles, and the circle will be positioned wherever v is fixed to. Exactly, yeah. If I fix u, that tells me where x and z will be fixed, and v is the one that will vary. Now, let me go back to this part right here. The domain. Okay. This is the surface is a cylinder surface when the domain of R is all of R2. And R2 really means the UV plane. I have no restrictions. I can plug in any UV point that I want. So this one, I'm going to have you guys discuss with your classmates. What will the surface be if the domain is UV points, but U only goes from 0 to pi over 2, and v only goes from 0 to 1. Okay? U is like your theta, okay? And v is what y is equal to. So with your group, just discuss, what do you think the surface would look like if we restricted the domain to just those bounds? Just check in with your classmates. How would that change the cylinder? Correct. I guess if you fix u, it fixes x and z, and then lets y vary. It changes where because the line should be this way. It changes where the line, like the line still gets oriented this way, but the x coordinate and the z coordinate of these points on this line are different from the x coordinate and y and z coordinate of the points on this line. And so you see how here we got this equation? If you fix v, then you end up with y is equal to v for a fixed x and z. So it is kind of hard to describe. I agree. The length of the line is given by that, because that's telling you how far y can go between what two values. So that's part of this question. Yeah, part of this question. All right, guys, let's see. So here are my bounds for u and v. If I bound u, which you think of theta, from 0 to pi over 2, notice that now the circle will only rotate on the xz plane from 0 to pi over 2. Right? So it's a quarter circle. Instead of full circles, you have quarter circles that vary. And y only will vary from 0 to 1. So you have this small sheet of paper like this. Okay? That's going to become relevant later. Right now is just so you see how that changes the surface. So the reason, so far when we've been doing surfaces, we've been doing either equations or we've been doing functions, right, for surfaces. The reason this is a little bit more powerful is because it gives you the entire surface, but then by changing the parameters of u and v, you can manipulate the surface to change it so that it's smaller or bigger according to how you want it. So it gives us more flexibility to alter the way the surface looks like. Bill?
If we can parameterize curves and surfaces, can we replicate it?
I believe so, yes. In this case, it's to be a three-dimensional point with three-dimensional vector. Yeah. Okay, so I'm going to show you more surfaces. They're going to be a little gnarly, but then I'm going to give you a tip on how to do it for the surfaces you use for integration, which were spheres, cylinders, paraboloid, like the stuff from chapter 15. Okay, I'm going to give you guys like a little shortcut on how to do it for those surfaces, but I want to just show you some more. So here's the cylinder one. There's a helix that can be parametrized. Notice this is definitely not a function. It fails the z vertical line test. Okay, but it lets you basically parametric surfaces are easier to like create easier with these parametric functions. Okay, I change the parameters and then that'll remove or add more pieces to the surface. What's this? Big old point. So that's a helix. With some bruises on it. Here's a surface. Okay. What do you guys notice about X, Y, and Z? That's right. It's using spherical coordinates. Why is it using spherical coordinates? Because I just need X, Y, and Z to be parameterized with the same two variables. And in spherical, they're parameterized by phi and theta, which are two variables. It's just that rho is 5 right now, so the radius is 5. We're gonna do a plane, right? Everything that we've learned, and then here I just want to show you a Mobius strip that can be parametrized. This pretty little Mobius strip here. Little ant started walking on here. It would walk throughout the entire surface of the Mobius strip. There is no two sides to a Mobius strip. Okay, so I just wanted to show you that. But now let's see how you're going to do it for the common surfaces that we've been using in this class. Okay. So parameterizing common surfaces. And what I mean by that are the ones that we've been using in this class. So let's start with spheres first. So given a sphere of radius r, we're going to end up using spherical coordinates. Let rho equal that r. And since in spherical coordinates, we know x is rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi. I use all this information to create a parametric equation. And what we're going to do is we're just going to let u equal phi and let v equal theta. And then we get r of uv. Since the radius is never going to change, r just becomes, rho just becomes that r. And so then we get sine of v, which is, we're going to let it be u, cosine v, r sine u sine v, and then r cosine. And that will guarantee that we parameterize a sphere of radius r. cylinders, like the one that we just did. So cylinders of the form. Let's do the cylinders that you guys have been dealing with. You've done things like x squared plus y squared is equal to some k squared. I don't want to use little r because we're using that for this. We just did one where it was x squared plus z squared is equal to some radius squared. And then you've also done y squared plus z squared.
With this fluid equation, it should be r cosine u for the z component.
Oh shit, thank you, yeah. Because it's phi, right? Yeah. Technically, guys, you don't have to always use u. You don't have to use u. I could do r of phi theta. There's just dummy variables. It's just that your textbook will use UVs for the upcoming stuff that you could figure out. But if on the test you wrote r, or let's say this was 7 sine phi cosine theta, totally got it. It just needs to be parameterized by 2 variables. Okay. For cylinders, for this cylinder x squared plus z squared, you wanted to use polar coordinates, right? Because it's a circle. So just use, let x be the radius cosine theta, and let z be the radius sine theta. Okay? So just like the problem that we did, that'll guarantee that you have a circle in relationship to x and y. And what's the circle is going to vary with respect to the other variable, which is z. So then you let z be the other variable. So you're going to get r of uv. You're going to use polar here. And this is a circle of radius. What's the radius of the circle? That'd be k. So you let x be cosine theta or cosine u with k in front of it. So it gives you the radius. K cosine u, k sine u. And then you just let z be that other free variable like that. That will guarantee that now it's circular in x and y, and the circles will shift up and down with respect to z, because that's the other free variable. If it's circular with respect to x and z, like the one we just did, x be cosine u, so that z be k sine u, and let the other variable vary by letting it be v. And then the last one, as you can expect, you're going to let y be k cosine u and z be k sine u. And then in this case, it's x that's varying. And that's circle is varying with respect to x in the x direction.
Which one would look to be k cosine u versus k sine u?
What do you mean, like if I swap these?
Yeah.
No, because this equation will still be true. Oh, that's the other thing, guys. A surface can be parameterized many different ways. We just have to find one way of doing it to give you a surface. All right. And then the last common surface are the ones of functions. So surfaces of functions that we did in chapter 14. So for a surface given by z equaling f of xy, since the goal is to get each of the variables in terms of two variables, notice that's z is already in terms of two variables, x and y, right? Since z is already expressed in terms of x and y, let x be u and let y be v, so that we get that the surface is parametrized by letting x be u, letting y be v, and letting z be whatever the expression of the function is. Let me show you a quick example. Let's say I gave you this function here. Right? That's a weird surface. Okay? But this is basically z. So what this is saying is that you can kind of cheat and make a vector function where you just let x be u, you let y be v, and then you let z be this, but switch it all the x's with u's and all the y's with v's. And that would parameterize that surface. Let's come up with that set. Say it again. For a surface of a function. Yeah, for a surface of a function. So let's say I have f of xy is xy squared sine of xy, right? That's this surface right here. Weird surface. So let me change this parameterization. Oh, by the way, if you want to parameterize on Desmos, you're going to do, just put your functions first. And when Desmos reads a u and a v, it knows you're doing a surface. Okay? U, v. See how I showed that already? Okay? And then uv squared minus sine of uv. And see, it's only giving me a piece of the surface because of the domain restriction. Let me go so that it's from negative 10 to 10, negative 10 to 10. See? That's so easy to manipulate a surface. Then just a function, it's too hard. It's not too hard, but it's not as easy. Sam? Is there a way to parameterize a two? It's kind of like what you're doing, but the two-dimensional, you mean a graph in 2 dimensions, right? Yeah. Which would be like a curve. Yeah. Do you mean like restricting the domain so that you're only using points on that circle? Is that what you mean? Yeah, because like, for example, in this example that we looked at, here's the UV plane, right? This restriction goes from 0 to pi over 2, and this goes from 0 to 1. So right now, that part of the cylinder that was like this is only being plotted from UV points that live in this rectangle. And from, I think what you're saying is, what if the UV points are only coming from here? Then it's going to give you some curve, though. It won't give you a surface. It'll give you some curve. Yeah. I believe so. I think that's what you're asking. Was it something different? Okay. But you can think, if I only do this, then it's just going to give me curves on my surface. And so it'll only show me particular curves on the surface. So it'd be like grid lines. Or it'd be kind of like, remember when you guys had level curves that were like kind of making up, they lived in the XY plane, but when you pick them up, then the curves themselves had depth now. And so then there were the curves related to the surface. That's kind of what would be happening. Okay. But yes, so I just wanted to show you guys that, just so you can see I can change all this stuff here. Oops, it's not showing me the surface, and I can manipulate it. Okay, it's really nice. It's really nice. All right. So I just have 3 problems for you guys to work on with the groups. Okay, and then we're free. I want you to practice. They're a little challenging. Okay, practice parametrizing a sphere, the surface of a function, and a plane. Okay. 1, 2, 3, 4, 5. Oh, my God, it doesn't. 1, 2, 3, 4. One right here. The solutions will be posted on the notes. It could be a little tough, so just please work with your classmates. Let me share my screen right now. Use the tips that I gave you here up on the board. Cool. You guys check in with each other. The first step is try to see how you can use this to start your final prediction. And just keep in mind that this sphere is centered at the origin. So you want to use it.
I think I remember. I'm just there's so many
So you got the sphere at the origin, right? And since it has radius 1, this point will be at 1, right? So if I shift the center 1 unit this way, it's going to move all the x coordinates 1 unit this way. So then that means that I'm going to want to add all of these by 1, so that all the x's will be where they originally were placed, but then add 1 to them. Like if the original x coordinate was here, I'm adding 1 to it so that it moves it 1 unit in the x direction. And then same argument for y and the same argument.
I didn't want to do it. It's too much effort. I didn't want to do that.
Guys, for number 3, you gotta remember how to find the equation of a plane. Equation of a plane, which I know you're all trying to avoid, but it'll be on the final, so you gotta make sure you know how to do it.
No water in this.
Do you want to go get something? Go. You know where the bathrooms were at?
Yeah.
But go downstairs. You can go.
Because it was be over, right?
That answer is totally allowed. It's allowed because each of these is a function you have like maybe sine u plus x or something. The sphere right now is radius 1. So before you shifted, all the points in the sphere were the original points. But if I shift the center so that x increases to 1, that's going to force the sphere, all the points in the sphere to also increase. So that means that wherever I mention they all for the point, yeah, for the point where there is a neighborhood.
Or it didn't even like swung out. For the other one, I had it so that dots can take the electrons. And I'm telling you, I don't know what it's called.
In physics, we do cross class. And they were switched around and it was, had minus J.
Oh, yeah, they
They do different physics, yeah. I haven't done it yet, but
So that part I won't show up here.
In chemistry, it's there are
As long as they're
That's A, B, and C, so.
Careful. Let me see. Okay, it's not updating yet. Oh, there we go. All right, guys. So for number 3, you should find the equation of the plane. And then once you find the equation of the plane, just get z by itself, so that you get z in terms of a function, and then you can just let x be u, y be v, and then your function. Oh shit! My bad. Thank you, Ted. It should be u. This one can be my bad. Okay. So 16.6, it's just this part. I'm splitting it into 2 pieces. And then when we come back after the break, we'll do the second piece. Okay? This is just the graphing part. The non-calculus part. All right. Early. All right. Not as early as I'd hope, but it's all good. That's it. We're done for today, okay? I combined the constants. Yeah.
That's right. Actually, found it.
Oh, okay, yeah. Oh, you can turn it in.
Okay.